a formula that we could write down from this theorem, the area of similar polygons, could be if I say the area of this first figure compared to the area of the second figure. This ratio should be equal to, if I have a side length and another side length, squared. An equivalent way to write this would be the side length squared over the side length squared. However you want to write this ratio, you can. But this could be a formula that you would deduce from here. The nice thing is that this applies to any similar polygons, not just quadrilaterals, not just the three that we looked at in the little exploration. This applies to anything. It applies to these hexagons. It could apply to octagons. As long as they're similar, this relationship holds. Okay. So we can use this to actually find some missing pieces. So we'll start with trying to find a missing area. So in here I tell you that these two figures are similar. I want you to find the missing area, in this case the area of the non-shaded. So I know the area of this. I'll call it X. So using this proportion, I could make a ratio of the areas. I could say X is to 3 as the side length ratio is 8 to 2 squared. To solve this algebraically, you can do a lot of things. I would recommend simplifying the ratio first and then squaring, because it'll make you can do this a lot easier. Well, you can do this in your head a lot more efficiently. So you can say 8 over 2 is the same as 4 over 1 squared. Or X over 3 equals 16 over 1. And how do you solve this proportion? Cross multiply. 1 times X is X. 3 times 16. X was an area, so we should have area units. You can play the same game here. We don't know what the area is, so call it a variable. Again, I'm going to set up my ratio of areas so that the variable is on top. That should be equal to the ratio of the side lengths. Squared. Again, I think it's much easier to reduce these numbers first. At this ratio, 10 over 18 reduces to what? 5 over 9 squared. And once this is reduced, I think squaring each of those you should be able to do this in your head. 5 squared is 25. 9 squared is 81. So you're really solving this proportion. 8 over 162 is 25 or 81. You can cross multiply and divide. You could also, if you're savvy, you would notice that 162 is just twice as big as 81. So X should be twice as big as 25, which is 50. X is 50 meters squared. You can also work this process in reverse. So if I tell you the areas, we can use that to find lengths. Like in part C here, again, I'll set up a ratio of the areas. And that should be equal to the ratio of the corresponding side length. So if I go the white rectangle, the shaded rectangle, I'll go white rectangle to shaded rectangle, but the side lengths are squared. You have a lot of choices to solve this algebraically. My recommendation to you would be to simplify any ratios you can. Note that 225 over 25 reduces to 9 over 1. And if you need to solve this ratio, 9 over 1 equals x over 6 squared. At this point, you could square top and bottom, cross multiply, and solve. I notice this as something squared is equal to some perfect squares. 9 and 1 are both perfect squares. So you could, at this point, also square root here. And get x over 6 is equal to, the square root of 9 is 3, square root of 1 is 1. And this ratio you can do without a calculator. X should be 18. Right. Would you like to do D on your own, or would you like me to do for you as one more example? All right, try this. Try D and E on your own. Come up with some answers, and if you have questions, I'll try to come around and help out.
It's 3 to 4.
Trust Spencer. Just trust him.
Yeah, I asked him yesterday why my grade is so good. I asked him about soccer grade and everything.
On that lesson, I trust that you got it.
I probably didn't. But whatever.
What you got?
We just did these.
Wait, it just gives it to you? Oh,